All right, new goal. One sec. Water. Sorry about that. Had to get a drink. Got a little bit of heartburn going. So I got a new goal. I need to add chemistry to my thing. So for OpenStax, I want to finish the chemistry one first. Because I think the school that I went to starts next week, from what a friend told me. So if what she says is right, then I'd like to have that done so I can start tutoring, maybe even as early as next week. I want to have the whole book read before I start tutoring, and then maybe some examples. So let's go ahead and do that. I'm going to go ahead and open up the OpenStax. Okay. Science, Chemistry 2E, PDF, go to File, and then we'll open this up. There, Chapter 2, Atoms, Molecules, and Ions. Okay, that should do it. Chapter outline, early ideas in atomic theory, evolution of atomic theory, atomic structure and symbolism, chemical formulas, periodic table, ionic and molecular compounds, chemical nomenclature. Introduction. Lung diseases and lung cancers are among the world's most devastating illnesses, partly due to delayed detection and diagnosis. Most non-invasive screening procedures aren't reliable, and patients often resist more accurate methods due to discomfort with the procedures or with the potential danger that the procedures cause. But what if you could be accurately diagnosed through a simple breath test? Early detection of biomarkers, substances that indicate an organism's disease or psychological state, could allow diagnosis and treatment before a condition becomes serious or irreversible. Recent studies have shown that your exhaled breath can contain molecules that may be biomarkers for recent exposure to environmental contaminants for the biological or pathological conditions ranging from asthma to lung cancer. Scientists are working to develop biomarker fingerprints that could be used to diagnose a specific disease based on the amounts and identities of certain molecules in a patient's exhaled breath. In Sangeeta Bhatia's lab at MIT, a team used substances that can react specifically inside diseased lung tissue. The products of the reactions will be present as biomarkers that can be identified through mass spectrometry, an analytical method discussed later in the chapter. A potential application would allow patients with early symptoms to inhale or ingest a sensor substance and minutes later to breathe into a detector for diagnosis. Similar research by scientists such as Laura Lopez Sanchez has provided similar processes for lung cancer. An essential concept underlying this goal is that a molecule's identity, which is determined by the numbers and types of atoms it contains and how they are bonded together. This chapter will describe some of the fundamental chemical principles related to the composition of matter, including those central to the concept of molecular identity. 21. Early ideas in atomic theory, learning objectives. By the end of this section, you will be able to state the postulates of Dalton's atomic theory, use postulates of Dalton's atomic theory to explain the laws of definite and multiple proportions. The earliest recorded discussion of the basic structure of matter comes from ancient Greek philosophers, the scientists of their day. In the 5th century BC, Leucippus and Democritus argued that all matter was composed of small, finite particles they called atomos, a term derived from the Greek word for indivisible. They thought of atoms as moving particles that differed in shape and size, and which could be joined together. Later, Aristotle and others came to the conclusion that matter consisted of various combinations of the 4 elements: fire, earth, air, and water, and could be infinitely divided. Interestingly, these philosophers thought about atoms and elements as philosophical concepts, but apparently never considered performing experiments to test their ideas. The Aristotelian view of the composition of matter held sway for over 2,000 years, until English schoolteacher John Dalton helped to revolutionize chemistry with his hypothesis that the behavior of matter could be explained using an atomic theory. First published in 1807, many of Dalton's hypotheses about the microscopic features of matter are still valid in modern atomic theory. Here are the postulates of Dalton's atomic theory. 1. Matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical change. 2. An element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of that element. A macroscopic sample of an element contains an incredibly large number of atoms. Element all of which have identical chemical properties. 3. Atoms of one element differ in properties from atoms of all other elements. 4. A compound consists of atoms of two or more elements combined in a small whole number ratio. In a given compound, the numbers of atoms of each of its elements are always present in the same ratio. 5. Atoms are neither created nor destroyed. What happened? Sorry, I'm having an issue. Atoms are neither created nor destroyed during a chemical change, but are instead rearranged to yield substances that are different from those present before the change. Oops, wrong. Sorry, I'm gonna plug the charger in and see if that helps with the stuttering right there. Yep. Okay. Right. Dalton's atomic theory provides a microscopic explanation of the many macroscopic properties of matter that you've learned about. For example, if an element such as copper consists of only one kind of atom, then it cannot be broken down into similar substances, that is, into substances composed of fewer types of atoms. And if atoms are neither created nor destroyed during a chemical change, then the total mass of matter present when matter changes from one type to another will remain constant. The law of conservation of matter. Dalton knew of the experiments of French chemist Joseph Proust, who demonstrated that all samples of a pure compound contain the same elements in the same proportion by mass. This statement is known as the law of definite proportions, or the law of constant composition. The suggestion that the numbers of atoms of the elements in a given compound always exist in the same ratio is consistent with these observations. For example, when different samples of isooctane, a component of gasoline, and one of the standards used in the octane rating system are analyzed, they are found to have a carbon to hydrogen mass ratio of 5.33 to 1, as shown in that table. It is worth noting that although all samples of a particular compound have the same mass ratio, the converse is not true in general. That is, samples that have the same mass ratio are not necessarily the same substance. For example, there are many compounds other than isooctane that have a carbon to hydrogen mass ratio of 5.33 to 1.00. Dalton also used data from Proust as well as results from his own experiments to formulate another interesting law. The law of multiple proportions states that when two elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in a small ratio. Whole numbers. For example, copper and chlorine can form a green crystalline solid with a mass ratio of 0.558 grams of chlorine to 1 gram of copper, as well as a brown crystalline solid with a mass ratio of 1.116 grams of chlorine to 1 gram of copper. These ratios by themselves may not seem particularly interesting or informative. However, if we take a ratio of these ratios, we obtain a useful and possibly surprising result, a small whole number ratio. 1.116 over 1 divided by 0.558 over 1 is 2 to 1. This 2 to 1 ratio means that The brown compound has twice the amount of chlorine per amount of copper as the green compound. This can be explained by atomic theory if the copper to chlorine ratio in the brown compound is 1 copper atom to 2 chlorine atoms, and the ratio in the green compound is 1 copper atom to 1 chlorine atom. The ratio of chlorine atoms, and thus the ratio of their masses, is therefore 2 to 1. 2.2, Evolution of Atomic Theory. Learning objectives. By the end of this section, you will be able to outline milestones in the development of modern atomic theory, summarize and interpret the results of the experiments of Thomson, Millikan, and Rutherford, describe the 3 subatomic particles that compose atoms, define isotopes, and give examples for several elements. If matter is composed of atoms, what are atoms composed of? Are they the smallest particles, or is there something smaller? In the late 1800s, a number of scientists interested in questions like these investigated the electrical discharges that could be produced in low-pressure gases, with the most significant discovery made by English physicist J.J. Thomson using a cathode ray tube. This apparatus consisted of a sealed glass tube from which almost all the air had been removed. The tube contained 2 metal electrodes. When high voltage was applied across the electrodes, a visible beam called a cathode ray appeared between them. This beam was deflected toward the positive charge and away from the negative charge, and was produced in the same way with identical properties. When different metals were used for the electrodes in similar experiments, the ray was simultaneously deflected by an applied magnetic field, and measurements of the extent of deflection and the magnetic field's strength allowed Thomson to calculate the charge to mass ratio of the cathode ray particles. The results of these measurements indicated that these particles were much lighter than atoms. Based on his observations, here is what Thomson proposed and why. The particles are attracted by positive charges and repelled by negative charges, so they must be negatively charged. Like charges repel and unlike charges attract. They are thus less massive than atoms and indistinguishable regardless of the source material, so they must be fundamental subatomic constituents of all atoms. Although controversial at the time, Thomson's idea was gradually accepted, and his cathode ray particle is what we now call an electron, a negatively charged subatomic particle with a mass more than 1,000 times less than that of an atom. The term electron was coined in 1891 by Irish physicist George Stoney from electric ion. In 1909, more information about the electron was uncovered by American physicist Robert A. Millikan via his oil drop experiments. Millikan created microscopic oil droplets which could be electrically charged by friction as they formed or by using X-rays. These droplets initially fell due to gravity, but their downward progress could be slowed or even reversed by an electric field lower in the apparatus, by adjusting the electric field strength and making careful measurements and appropriate calculations. Millikan was able to determine the charge on individual drops. Looking at the charge data that Millikan gathered, you may have recognized that the charge of an oil droplet is always a multiple of a specific charge, 1.6 times 10 to the negative 19 coulombs. Millikan concluded that this value must therefore be a fundamental charge, the charge of a single electron, with his measured charges due to an excess of 1 electron, 2 electrons, 3 electrons, and it's just multiples of 1.6 times 10 to the negative 19, and so on a given oil droplet. Since the charge of an electron was now known due to Millikan's research, and the charge to mass ratio was already known due to Thomson's research, 1.759 times 10 to the 11 coulomb per kilogram, it only required a simple calculation to determine the mass of the electron as well. Mass of an electron equals 1.602 times 10 to the negative 19 coulomb times 1 kilogram over 1.759 times 10 to the 11 coulombs equals 9.107 times 10 to the negative 31 kilograms. Scientists had now established that the atom was not divisible, as Dalton had believed, and due to the work of Thomson, Millikan, and others, the charge and mass of the negative subatomic particles, the electrons, were known. However, the positively charged part of an atom was not yet well understood. In 1904, Thomson proposed the plum pudding model of atoms, which described a positively charged mass with an equal amount of negative charge in the form of electrons embedded in it. Since all atoms are electrically neutral, a competing model had been proposed in 1903 by Huntaro Nagaoka, who postulated a Saturn-like atom consisting of a positively charged sphere surrounded by a halo of electrons. The next major development in understanding the atom came from Ernest Rutherford, a physicist from New Zealand who largely spent his scientific career in Canada and England. He performed a series of experiments using a beam of high-speed, positively charged alpha particles that were produced by the radioactive decay of radium. Alpha particles consist of two protons and two neutrons. Rutherford and his colleagues Hans Geiger and Ernest Marston aimed a beam of alpha particles, the source of which was embedded in a lead block to absorb most of the radiation, at a very thin piece of gold, and examined the resultant scattering of the alpha particles using a luminescent screen that glowed briefly where hit by an alpha particle. What did they discover? Most particles passed right through the foil without being deflected at all. However, some were diverted slightly, and a very small number were deflected almost straight back toward the source. Rutherford described finding these results. It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Yeah, that is true. Yep, so this is what it looks like. The laser's in the box. Looks like a lead line box. So I'm guessing the lead lining is able to keep the particles from, or to almost ensure that the particles will go out one end. And then it's going to go into, um, oh, okay, so that's interesting. Okay. I might have to try this experiment. That'd be pretty sweet. Oh my gosh, shining lasers at that? Oh, that'd be so sick. Okay, that actually could be fun. So I just need to find a way to do that. Dark room. Maybe hang it. Oh, put it on a pendulum. A laser on a pendulum, and then one of these systems on a pendulum. That'd be hilarious. Okay. Interesting. That's really cool. I got some ideas. That's why I love this stuff. Here's what Rutherford deduced. Because most of the fast-moving alpha particles pass through the gold atoms undeflected, they must have traveled through essentially empty space inside the atom. Alpha particles are positively charged, so deflections arose when they encountered another positive charge. Like charges repel each other. Since like charges repel one another, the few positively charged alpha particles that changed paths abruptly must have hit or closely approached another body that also had a highly concentrated positive charge. Since the deflections occurred a small fraction of the time, this charge only occupied a small amount of the space in the gold foil. Analyzing a series of experiments in detail, Rutherford drew two conclusions. One, the volume occupied by an atom must consist of a large amount of empty space. Two, a small, relatively heavy, positively charged body, the nucleus, must be at the center of each atom. This analysis led Rutherford to propose a model in which an atom consists of a very small, positively charged nucleus in which most of the mass of the atom is concentrated, surrounded by the negatively charged electrons, so that the atom is electrically neutral. After many more experiments, Rutherford also discovered that the nuclei of other elements contain the hydrogen nucleus as a building block, and he named this more fundamental particle the proton. The positively charged subatomic particle found in the nucleus, with one addition, which you will learn next. This nuclear model of the atom proposed over a century ago is still used today. Another important finding was the discovery of isotopes. During the early 1900s, scientists identified several substances that appeared to be new elements, isolating them from radioactive ores. For example, a new element produced by the radioactive decay of thorium was initially given the name mesothorium. However, a more detailed analysis showed that mesothorium was chemically identical to radium, another decay product, despite having a different atomic mass. This results, along with similar findings for other elements, led the English chemist Frederick Soddy to realize that an element could have types of atoms with different masses that were chemically indistinguishable. These different types are called isotopes, atoms of the same elements that differ in mass. Soddy was awarded the Nobel Prize in Chemistry in 1921 for this discovery. One puzzle remained. The nucleus was known to contain almost all of the mass of an atom, but the number of protons only provided half or less of that mass. Different proposals were made to explain what constituted the remaining mass, including the existence of neutral particles in the nucleus. As you might expect, detecting uncharged particles is very challenging, and it was not until 1932 that James Chadwick found evidence of neutrons, uncharged subatomic particles with a mass appropriately the same as that of protons. The existence of the neutron also explains isotopes. They differ in mass because they have different numbers of neutrons, but they are chemically identical because they have the same number of protons. This will be explained in more detail later in this chapter. 2.3 Atomic Structure and Symbolism. Learning objectives. By the end of this section, you will be able to write and interpret symbols that depict the atomic number, mass number, and charge of an atom or ion, define the atomic mass unit and average atomic mass, calculate average atomic mass and isotope abundance. The development of modern atomic theory revealed much about the inner structure of atoms. It was learned that an atom contains a very small nucleus composed of positively charged protons and uncharged neutrons, surrounded by a much larger volume of space containing negatively charged electrons. The nucleus contains the majority of an atom's mass because protons and neutrons are much heavier than electrons, whereas electrons occupy almost all of an atom's volume. The diameter of an atom is on the order of 10 to the negative 10 meters, whereas the diameter of the nucleus is roughly 10 to the negative 15 meters, about 100,000 times smaller. For a perspective about their relative sizes, consider this. If the nucleus were about the size of a blueberry, the atom would be about the size of a football stadium. Atoms and the protons, neutrons, and electrons that compose them are extremely small. For example, a carbon atom weighs less than 2 times 10 to the negative 23 grams, and an electron has a charge of less than 2 times 10 to the negative 19 coulombs. When describing the properties of tiny objects such as atoms, we use appropriately small units of measure, such as the atomic mass unit and the fundamental unit of charge. The AMU was originally defined based on hydrogen, the lightest element, then later in terms of oxygen. Since 1961, it has been defined with regard to the most abundant isotope of carbon, atoms of which are assigned masses of exactly 12 AMU. Thus, 1 AMU is exactly 1/12 of the mass of one carbon-12 atom. 1 AMU equals 1.6605 times 10 to the negative 24 grams. The Dalton and the unified atomic mass unit are alternative units that are equivalent to the AMU. The fundamental unit of charge, also called the elementary charge, equals the magnitude of the charge of an electron, with E equals 1.602 times 10 to the negative 19 coulombs. A proton has a mass of 1.0073 AMU and a charge of +1. A neutron is a slightly heavier particle with a mass of 1.0087 AMU and a charge of 0. As its name suggests, it is neutral. The electron has a charge of -1 and is a much lighter particle with a mass of about 0.00055 AMU. It would take about 1,800 electrons to equal the mass of one proton. The properties of these fundamental particles is summarized. Hold on one second. Three million Earths. Oh, never mind. Okay, that's a different ratio. Okay, sorry. I just wanted to look up the ratio and see if they were similar. They're not. The properties of these fundamental particles are summarized in Table 2.2. An observant student might notice that the sum of an atomic subatomic particles does not equal the atomic's actual mass. The total mass of 6 protons, 6 neutrons, and 6 electrons is 12.0993 AMU, slightly larger than 12.00 AMU. This missing mass is known as the mass defect, and you will learn about it in the chapter on nuclear chemistry. Oh, I cannot wait to figure out what the hell that is. I always was confused by that. The number of protons in the nucleus of an atom is its atomic number Z. This is the defining trait of an element. Its value determines its identity of the atom. For example, any atom that contains 6 protons is the element carbon and has the atomic number 6. Regardless of how many neutrons or electrons it may have, a neutral atom must contain the number of positive and negative charges, so the number of protons equals the number of electrons. Therefore, the atomic number also indicates the number of electrons in an atom. The total number of protons and neutrons in an atom is called its mass number. The number of neutrons is therefore the difference between the mass number and the atomic number, A to Z, number of neutrons. Atoms are generally or electrically neutral if they contain the same number of positively charged protons and negatively charged electrons. When the numbers of these subatomic particles are not equal, the atom is electrically charged and is called an ion. The charge of an atom is defined as follows. Atomic charge equals number of protons minus number of electrons. As will be discussed in more detail later in this chapter, atoms and molecules typically acquire charge by gaining or losing electrons. An atom that gains one or more electrons will exhibit a negative charge and is called an anion. Positively charged atoms called cations are formed when the atom loses one or more electrons. For example, a neutral sodium atom, Z equals 11, has 11 electrons. If this atom loses one electron, it will become a cation with 1 plus charge. 11 minus 1 equals 1 plus. A neutral oxygen from Z equals 8 has 8 electrons, and if it gains 2 electrons, it will become an anion with a 2 minus charge. 8 minus 10 equals 2 minus. Ooh. Yikes. The addition of small amounts of iodine to table salt, iodized salt, has essentially eliminated this health concern in the United States. Oh, sorry. Chemical symbols. A chemical symbol is an abbreviation that we use to indicate an element or an atom of an element. For example, the symbol of mercury is Hg. We use the same symbol to indicate one atom of mercury or to label the container of many atoms of the element mercury in the macroscopic domain. The symbols for several common elements and their atoms are listed in Table 2.3. The symbols are some symbols are derived from common name of the element. Others are abbreviations of the name in another language. Most symbols have 1 or 2 letters, but 3-letter symbols have been used to describe some elements that have atomic numbers greater than 112. To avoid confusion with other notations, only the first letter of the symbol is capitalized. For example, CO is a symbol for the element cobalt, but cap C, capo, is the notation for the compound carbon monoxide, which contains atoms of the elements carbon, C, and oxygen, O. All known elements and their symbols are in the periodic table in figure 2.26. Traditionally, the discoverer or discoverers of a new element names the element. However, until the name is recognized by the International Union of Pure and Applied Chemistry, the recommended name of the new element is based in the Latin words for its atomic number. For example, element 106 was called unhilhexium, element 107 was called unilseptium, and element 108 was called uniloctium for several years. These elements are now named after scientists or occasionally locations. For example, element 106 is known as Seaborgium in honor of Glenn Seaborg, a Nobel Prize winner who was active in the discovery of several heavy elements. Element 109 was named in honor of Lise Meitner, who discovered nuclear fission, a phenomenon that would have world-changing impacts. Meitner also contributed to the discovery of some major isotopes, discussed immediately below. Isotopes. The number for The symbol for a specific isotope of any element is written by placing the mass number as a superscript to the left of the element symbol. The atomic symbol is sometimes written as a superscript or subscript preceding the symbol, but since this number defines the element's identity, as does its symbol, it is often omitted. For example, magnesium exists as a mixture of three isotopes, each with an atomic number of 12 and with mass numbers of 24, 25, and 26, respectively. These isotopes can be identified as 24 magnesium, 25 magnesium, and 26 magnesium. These isotope symbols are read as element mass number and can be symbolized consistent with this reading. For instance, 24 magnesium is read magnesium 24 and can be written as magnesium 24 or Mg24. Magnesium 25 is read as magnesium 25 and can be written as magnesium 25 or Mg25. All magnesium atoms have 12 protons in their nucleus. They differ only because a magnesium atom has 12 neutrons in its nucleus. A 25 milligram atom has 13 neutrons, and a 26 milligram has 14 neutrons. Information about the naturally occurring isotopes of elements with atomic numbers 1 through 10 is given in Table 2.4. Note that in addition to standard names and symbols, the isotopes of hydrogen are often referred to using common names and accompanying symbols. Hydrogen 2, symbolized 2H, is also called deuterium and sometimes symbolized by D. Hydrogen 3, symbolized 3H, is also called tritium and sometimes symbolized T. Atomic mass. Because each proton and each neutron contribute approximately 1 AMU to the mass of an atom, and each electron contributes far less, the atomic mass of a single atom is approximately equal to its mass number, a whole number. However, the average masses of atoms of most elements are not whole numbers because most elements exist naturally as mixtures of two or more isotopes. The mass of an element shown in a periodic table or listed in a table of atomic masses is weighted averaged mass of all the isotopes present in a naturally occurring sample of that element. This is equal to the sum of each individual isotope's mass multiplied by its fractional abundance. Average mass equals, and then that's the sum of the fractional abundance times the isotopic mass indexed, all multiplied by each other. So for example, the element boron is composed of two isotopes. About 19.9% of all boron atoms are 10B with a mass of 10.0129 AMU, and the remaining 80.1% are 11B with a mass of 11.0093 AMU. The average atomic mass for boron is calculated to be, and then there's the calculation. It is important to understand that no single boron atom weighs exactly 10.8 AMU. 10.8 is the average mass of all boron atoms, and individual boron atoms weigh either approximately 10 AMU or 11 AMU. We can also do variations of this type of calculation as shown in the next example. As you will learn, isotopes are important in nature and especially in human understanding of science and medicine. Let's consider just one natural stable isotope, oxygen 18, which is noted in the table above and is referred to as one of the environmental isotopes. It is important in paleoclimatology, for example, because scientists can use the ratio between oxygen 18 and oxygen 16 in an ice core to determine the temperature of precipitation over time. Oxygen 18 was also critical to the discovery of metabolic pathways and the mechanisms of enzymes. Mildred Cohn pioneered the usage of these isotopes to act as tracers so that researchers would follow their path through reactions and gain a better understanding of what is happening. One of her first discoveries provided insight into the phosphorylation of glucose that takes place in the mitochondria, and the methods of using isotopes for this research contributed to entire fields of study. The occurrence in natural abundances of isotopes can be experimentally determined using an instrument called a mass spectrometer. Mass spectrometry is widely used in chemistry, forensics, medicine, environmental science, and many other fields to analyze and help identify the substances in a sample of material. In a typical mass spectrometer, the sample is vaporized and exposed to a high-energy electron beam that causes the sample's atoms or molecules to become electrically charged. Typically, by losing one or more electrons, these cations then pass through a variable electric or magnetic field that deflects each cation's path to an extent that depends on both its mass and charge. Similar to how the path of a large steel ball rolling past a magnet is deflected to a lesser extent than that of a small steel ball. The ions are detected, and a plot of the relative number of ions generated versus their mass-to-charge ratios, a mass spectrum, is made. The height of each vertical figure or peak in a mass spectrum is proportional to the fraction of cations with a specified mass-to-charge ratio. Since its initial use during the development of modern atomic theory, MS has evolved to become a powerful tool for chemical analysis in a wider range of applications. 2.4, chemical formulas. Learning objectives. By the end of this section, you'll be able to symbolize the composition of molecules using molecular formulas and empirical formulas, represent the bonding arrangement of atoms within molecules using structural formulas. A molecular formula is a representation of a molecule that uses chemical symbols to indicate the types of atoms, followed by subscripts to show the number of atoms of each type in a molecule. A subscript is used only when more than one atom of a given type is present. Molecular formulas are also used as abbreviations for the names of compounds. The structural formula for a compound gives the name same information as its molecular formula. The types and numbers of atoms in the molecule. One sec. But also shows how the atoms are connected in this molecule. The structural formula for methane contains symbols for one carbon atom and 4 hydrogen atoms, indicating the number of atoms in the molecule. The lines represent bonds that hold the atoms together. A chemical bond is an attraction between atoms or ions that holds them together in a molecule or a crystal. We will discuss chemical bonds and see how to predict the arrangement of atoms in a molecule later. For now, simply know that the lines are an indication of how the atoms are connected in a molecule. A ball and stick model shows the geometric arrangement of the atoms with atomic sizes not to scale, and a space-filling model shows the relative sizes of the atoms. Although many elements consist of discrete individual atoms, some exist as molecules made up of 2 or more atoms of the element chemically bonded together. For example, most samples of the elements hydrogen, oxygen, and nitrogen are composed of molecules that contain 2 atoms each, called diatomic molecules, and thus have the molecular formulas H2, O2, and N2 respectively. Other elements commonly found as diatomic molecules are fluorine, chlorine, bromine, and iodine. The most common form of the element sulfur is composed of molecules that consist of 8 atoms of sulfur. Its molecular formula is S8. It is important to note that a subscript following a symbol and a number in front of a symbol do not represent the same thing. For example, H2 and 2H represent distinctly different species. H2 is a molecular formula. It represents a diatomic molecule of hydrogen consisting of 2 atoms of the elements that are chemically bonded together. The expression 2H, on the other hand, indicates 2 separate hydrogen atoms that are not combined as a unit. The expression 2H2 represents 2 molecules of diatomic hydrogen. Compounds are formed when 2 or more elements chemically combine, resulting in the formation of bonds. For example, hydrogen and oxygen can react to form water, and sodium and chlorine can react to form table salt. We sometimes describe the composition of these compounds with an empirical formula, which indicates the types of atoms present and the simplest whole number ratio of the number of atoms or ions in the compound. For example, titanium dioxide, used as pigment in white paint and in the thick white blocking type of sunscreen, has an empirical formula of TiO2. This identifies the elements titanium and oxygen as the constituents of titanium dioxide and indicates the presence of twice as many atoms of the element oxygen as atoms of the element titanium. As discussed previously, we can describe a compound with a molecular formula in which the subscripts indicate the actual numbers of atoms of each element in a molecule of the compound. In many cases, the molecular formula of a substance is derived from experimental determination of both its empirical formula and its molecular mass, the sum of atomic masses for all atoms composing the molecule. For example, it can be determined experimentally that benzene contains two elements, carbon and hydrogen, and that every carbon atom in benzene there is one hydrogen atom. Thus, the empirical formula is CH. An experimental determination of the molecular mass reveals that a molecule of benzene contains 6 carbon atoms and 6 hydrogen atoms, so the molecular formula for benzene is C6H6. If we know a compound's formula, we can easily determine the empirical formula. This is somewhat of an academic exercise. The reverse chronology is generally followed in practice. For example, the molecular formula for acetic acid, the component that gives vinegar its sharp taste, is C2H4O2. This formula indicates that a molecule of acetic acid contains 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. The ratio of atoms is 2 to 4 to 2. Dividing by the lowest common denominator gives the simplest whole number ratio of atoms, 1 to 2 to 1. So the empirical formula is CH2O. Note that molecular formula is always a whole number multiple of an empirical formula. Man, I can't wait to talk about some of these things that I've been thinking about. Because what happens is as I'm reading these things, I get these ideas in my head. I make these connections with other ideas. So like one of the, for example, for the idea lightning is the idea I get because when I think of chemicals or compounds or covalent compounds, we'll get into that in a bit. Basically, the electrons are shared between two atoms. But what does that sharing look like? And the problem is on paper, we draw it either with little dots that show the connection between the two, which is a better representation. But in a lot of things, like here, we see lines drawn. And it's not the electrons themselves that are causing the atoms to be held together. It's the atoms being close enough together to essentially their waves overlap in such a way that, or their magnetic fields, I guess, would overlap in such a way that it would create a sort of node that traps the what we call electrons, the electrical energy, in that little area. And until the energy outside of it is enough to break that barrier, then the bond stays together. So if you can predict another compound with the formula C2H4O2 could exist, then you demonstrated good chemical insight and are correct. 2 C atoms and 4 H atoms and 2 O atoms can also be arranged to form a methyl formate, which is used in manufacturing as an insecticide and for quick drying finishes. Methyl formate molecules have one of the oxygen atoms between the 2 carbon atoms, differing from the arrangement in acetic acid molecules. I got to take one of my heartburn things. This is really annoying. I can't just drink a whole gallon of water tonight. There we go. Acetic acid and methyl formate are examples of isomers, compounds with the same chemical formula but different molecular structures. Note that this difference in the arrangement of the atoms has sorry, I lost my a major effect on their respective chemical properties. You would certainly not want to use a solution of methyl formate as a substitute for a solution of acetic acid when you make salad dressing. Many types of isomers exist. Acetic acid and methyl formate are structural isomers, compounds in which the molecules differ and how the atoms are connected to each other. There are also various types of spatial isomers, in which the relative orientations of the atoms in space can be different. For example, the compound carvone consists of 2 isomers that are mirror images of each other. S or plus carvone smells like caraway, and R minus carvone smells like spearmint. Hey, I've done that. I love that stuff. Yeah, you crush it up and then you you extract an oil out of it. 2.5 Periodic Table. Learning objectives. By the end of this section, you'll be able to state the periodic law and explain the organization of elements in the periodic table, predict the general properties of elements based on their location within the periodic table, identify metals, nonmetals, and metalloids by their properties and or location on the periodic table. As early chemists worked to purify ores and discovered more elements, they realized that various elements could be grouped together by their similar chemical behaviors. One such grouping includes lithium, sodium, and potassium. These elements are all shiny, conduct heat and electricity well, and have similar chemical properties. A second grouping includes calcium, strontium, and barium, which also are shiny, good conductors of heat and electricity, and have chemical properties in common. However, the specific properties of these two groupings are notably different from each other. For example, lithium, sodium, and potassium are much more reactive than are calcium, strontium, and barium. Lithium, sodium, and potassium form compounds with oxygen in a ratio of 2 of their atoms to 1 oxygen atom, whereas Ca, Sr, and Ba form compounds with 1 of their atoms to 1 oxygen atom. Fluorine, chlorine, bromine, and iodine also exhibit similar properties to each other, but these properties are drastically different from those of any of the elements above. I need to text my friend Josh real quick. So I'm gonna pause. Be right back. I decided to hold off on the text. I forget. I need to keep some things to myself for a little while to let it sort of settle in, especially newer ideas that I haven't really thought all the way through yet. But this one's pretty exciting, though. I'll just mention it here, just because. Oh no! Don't tempt me. Okay. Let's restart this again. As early chemists worked to purify ores and discovered more elements, they realized that various elements could be grouped together by their similar chemical behaviors. One such grouping includes lithium, sodium, and potassium. These elements are all shiny, conduct heat and electricity well, and have similar chemical properties. A second grouping includes calcium, strontium, and barium, which are also shiny, good conductors of heat and electricity, and have chemical properties in common. However, the specific properties and of these groupings are notably different from each other. For example, lithium, sodium, and potassium are much more reactive than are calcium, strontium, and barium. Lithium, sodium, and potassium form compounds with oxygen in a ratio of 2 of their atoms to 1 oxygen atom, whereas calcium, strontium, and barium form compounds with 1 of their atoms to 1 oxygen atom. Fluorine, chlorine, bromine, and iodine also exhibit similar properties to each other, but these properties are drastically different from those of any of the elements above. Dmitry Mendeleev, in 1869, and Lothar Meyer in Germany, 1870, independently recognized that there was a periodic relationship among the properties of the elements known at that time. Both published tables with the elements arranged according to increasing atomic mass, but Mendeleev went one step further than Meyer. He used his table to predict the existence of elements that would have the properties similar to aluminum and silicon, but were yet unknown. The discoveries of gallium and germanium, provided great support for Mendeleev's work, although Mendeleev and Meyer had a long dispute over priority. Mendeleev's contributions to the development of the periodic table are now more widely recognized. By the 20th century, it became apparent that the periodic relationship involved atomic numbers rather than atomic masses. The modern statement of this relationship, the periodic law, is as follows. The properties of the elements are periodic functions of their atomic numbers. A modern periodic table arranges the elements in increasing order of their atomic numbers and groups atoms with similar properties in the same vertical column. Each box represents an element and contains its atomic number, symbol, average atomic mass, and sometimes name. The elements are arranged in 7 horizontal rows called periods or series and 18 vertical columns called groups. Groups are labeled at the top of each column. In the United States, the labels traditionally were numerals with capital letters. However, IUPAC recommends that the numbers 1 through 18 be used, and these labels are more common. For the table to fit on a single page, parts of 2 of the rows A total of 14 columns are usually written below the main body of the table. I'm going to go ahead and just read it real quick. Hydrogen, helium, and it's read in row order. So row 1 is hydrogen, helium. Row 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. 3 is sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Row 4 is potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton. Row 5, rubidium, strontium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon. Row 6, cesium, barium, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, thallium, lead, bismuth, polonium, astatine, radon, francium, radium, actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium. Shit, sorry. Sharp pain in my finger. That hurt. Hold on. Oh, sorry. That was extremely painful. Sent a sharp pain through my whole body, but it was focused at my fingertip. That was super weird. Ow. I just realized I'm not wearing my glasses. That's all right. I'll wear them in a bit. Shoot, where was I? Mercury, thallium, lead, bismuth, polonium, astatine, radon. Oh, sorry. Berkelium, californium, einsteinium, fermium, mendeleevium, nobelium, lawrencium. Rutherfordium, dubnium, seaborgium, borium, hafnium, meitnerium, darmstadtium, rontgenium, copernicium, nihonium, fluorovium, moscovium, livermorium, tennessine, oganesson. Even after the periodic nature of elements and the table itself were widely accepted, gaps remained. Mendeleev had predicted, and other groups, including Henry Moseley, had later confirmed that there should be elements below manganese in group 7. German chemists Ida Taka and Walter Noddack set out to find the elements, a quest being pursued by scientists around the world. Their method was unique in that they did not only consider the properties of manganese, but also the elements horizontally adjacent to the missing elements 43 and 75 of the table. Thus, by investigating ores containing minerals of ruthenium, tungsten, osmium, and so on, they were able to identify naturally occurring elements that helped complete the table. Rhenium, one of their discoveries, was one of the last natural elements to be discovered and is the last stable element to be discovered. Francium, the last natural element to be discovered, was identified by Margaret Perry in 1939. Many elements differ dramatically in their chemical and physical properties, but some elements are similar in their behaviors. For example, many elements appear shiny or malleable, able to be deformed without breaking, and ductile, can be drawn into wires, and conduct heat and electricity well. Other elements are not shiny, malleable, or ductile, and are poor conductors of heat and electricity. We can sort the elements into large classes with common properties. Metals, elements that are shiny, malleable, good conductors of heat and electricity, shaded yellow. Nonmetals, elements that appear dull, poor conductors of heat and electricity, shaded green. And metalloids, elements that conduct heat and electricity moderately well and possess some properties of metals and some properties of nonmetals, shaded purple. Okay. The elements can also be classified into the main group elements or representative elements in the common columns labeled 1, 2, and 3 to 18. The transition metals in the columns labeled 3 to 12, and intermetals in that 2 rows at the bottom of the table. The top 2 elements are called lanthanides, and the bottom two elements are actinides. The elements can be subdivided further by more specific properties, such as the composition of the compounds they form. For example, the elements in group 1, the first column, form compounds that consist of one atom of the element and one atom of hydrogen. These elements, except hydrogen, are known as alkali metals, and they all have similar chemical properties. The elements in group 2, the second column, form compounds consisting of one atom of the element and two atoms of hydrogen. These are called alkaline earth metals, with similar properties among members of that group. Other groups with specific names are the pnictogens, group 15, the chalcogens, group 16, the halogens, group 17, and the noble gases, group 18, also known as inert gases. The groups can also be referred to by the first element of the group. For example, the chalcogens can be called the oxygen group or oxygen family. Hydrogen is a unique nonmetallic element with properties similar to both group 1 and group 17 elements. For that reason, hydrogen may be shown at top of both groups or by itself. As you will learn in your further study of chemistry, elements and groups often behave in somewhat similar manner. This is partly due to the number of electrons in their outer shell and their similar readiness to bond. These shared properties can have far-ranging implications in nature, science, and medicine. For example, when Gertrude Elion and George Hitchens were investigating ways to interrupt cell and virus replication to fight diseases, they utilized the similarity between sulfur and oxygen, both in group 16, and their capacity to bond in similar ways. Elion focuses on purines, which are key components of DNA and which contain oxygen, and she found that by introducing sulfur-based compounds called purine analogs that mimic the structure of purines, molecules with DNA would bond to the analogs rather than the regular DNA purine. With the normal DNA bonding and structure altered, Elion successfully interrupted cell replication. At its core, the strategy worked because of the similarity between sulfur and oxygen. Her discovery led directly to important treatments for leukemia. Overall, Elion's work with George Hitchens not only led to more treatments, but also changed the entire methodology of drug development. By using specific elements and compounds to target specific aspects of tumor cells, viruses, and bacteria, they laid the groundwork for many of today's most common and important medicines used to help millions of people each year. They were awarded the Nobel Prize in 1988. In studying the periodic table, you might have noticed something about the atomic masses of some of the elements. Element 43, technetium, element 61, promethium, and most of the elements with atomic number 84, polonium. Oh my god. Sorry. And higher have their atomic mass given in square brackets. This is done for elements that consist entirely of unstable radioactive isotopes. You will learn more about radioactivity in the nuclear chemistry chapter. An average atomic weight cannot be determined for these elements because their radioisotopes may vary significantly in relative abundance, depending on the source, or may not even exist in nature. The number in square brackets is the atomic mass number, an approximate atomic mass of the most stable isotope of that element. 2.6. Ionic and molecular compounds. Learning objectives. By the end of this section, you will be able to define ionic and molecular covalent compounds, predict the type of compounds formed from elements based on their location within the periodic table, determine formulas for simple ionic compounds. In ordinary chemical reactions, the nucleus of each atom, and thus the identity of the element, remains unchanged. Electrons, however, can be added to atoms by transfer from other atoms, lost by transfer to other atoms, or shared with other atoms. The transfer and sharing of atoms or electrons among atoms govern the chemistry of the elements. During the formation of some compounds, atoms gain or lose electrons and form electrically charged particles called ions. You can use the periodic table to predict whether an atom will form an anion or a cation, and you can often predict the charge of the resulting ion. Atoms of many main group metals lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. To illustrate, an atom of an alkali metal, group 1, loses one electron and forms a cation of +1 charge. An alkaline earth metal, group 2, loses 2 electrons and forms a cation with a +2 charge, and so on. For example, a neutral calcium atom with 20 protons and 20 electrons readily loses 2 electrons. This results in a cation with 20 protons, 18 electrons, and a +2 charge. It has the same number of electrons as atoms of the preceding noble gas, argon, and is symbolized ch2+. The name of a metal ion is the same as the name of the metal atom from which it forms, so calcium 2 is called a calcium ion. When atoms of nonmetal elements form ions, they generally contain enough electrons to give them the same number of electrons as an atom of the next noble gas. In the periodic table, atoms of group 17 gain 1 electron and form anions with a -1 charge. Atoms of group 16 gain 2 electrons and form ions with a 2- charge, and so on. For example, the neutral bromine atom with 35 protons and 35 electrons can gain 1 electron to provide it with 36 electrons. This results in an anion with 35 protons, 36 electrons, and a -1 charge. It has the same number of electrons as atoms of the noble gas, krypton, and is symbolized Br. A discussion of the theory supporting the favored status of noble gas electron numbers reflected in these predictive rules for ion formation is provided in a later chapter for this text. Note that usefulness of the periodic table in predicting likely ion formation and charge. Moving from the far left to the right on that periodic table, main group elements tend to form cations with a charge equal to the group number. That is, group 1 elements form +1 ions, group 2 elements form +2 ions, and so on. Moving from the far right to the left on the periodic table, elements often form anions with a negative charge equal to the number of groups moved left from the noble gases. For example, group 17 elements, one group left of the noble gases forms -1 ions. Group 16 elements, two groups left, form 2- ions, and so on. This trend can be used as a guide in many cases, but its predictive value decreases when moving toward the center of the periodic table. In fact, transition metals and some other metals often exhibit variable charges that are not predictable by their location in the table. For example, copper can form ions with a +1 or +2 charge, and iron can form ions with a +2 or +3 charge. The ions that we have discussed so far are called monatomic ions. That is, they are ions formed from only one atom. We also find many polyatomic ions. These ions, which act as discrete units, are electrically charged molecules, a group of bonded atoms with a overall charge. Some of the more important polyatomic ions are listed in Table 2.5. Oxyanions are polyatomic ions that contain one or more oxygen atoms. At this point in your study of chemistry, you should memorize the names, formulas, and charges of the most common polyatomic ions because you will use them repeatedly. They will soon become familiar. Okay, I'll go ahead and read these. Ammonium, hydronium, peroxide, hydroxide, acetate, cyanide, azide, carbonate, bicarbonate, nitrate, nitrite, sulfate, hydrogen sulfate, sulfite, hydrogen sulfite, phosphate, hydrogen phosphate, dihydrogen phosphate, perchlorate, chlorate, chlorite, hypochlorite, chromate, dichromate, permanganate. Note that there is a system for naming some polyatomic ions. Ate and ite are suffixes designating polyatomic ions containing more or fewer oxygen atoms. Per, short of hyper, and hypo, meaning under, are prefixes meaning more oxygen atoms than ate and fewer oxygen atoms than ite, respectively. For example, perchlorate is ClO4, chlorate is ClO3, chlorite is ClO2, and hypochlorite is ClO. Unfortunately, the number of oxygen atoms corresponding to a suffix given or a prefix is not consistent. For example, nitrate is an NO3-, while sulfate is SO4-2-. This will be covered in more detail in the next module on nomenclature. The nature of the attractive forces that hold atoms or ions together within a compound is the basis for classifying chemical bonding. When electrons are transferred in ions form, ionic bonds result. Ionic bonds are electrostatic forces of attraction, that is, the attractive forces experienced between objects of opposite electrical charge, in this case, cations and anions. When electrons are shared and molecules form, covalent bonds result. Covalent bonds are the attractive forces between the positively charged nuclei of the bonded atoms and one or more pairs of electrons that are located between the atoms. Compounds are classified as ionic or molecular on the basis of the bonds present in them. Ionic compounds, when an element composed of atoms that readily lose electrons, a metal reacts with an element composed of atoms that readily gain electrons, a nonmetal. A transfer of electrons usually occurs, producing ions. The compound formed by this transfer is stabilized by the electrostatic attractions, ionic bonds, between the ions of opposite charge present in the compound. For example, when each sodium atom in a sample of sodium metal, group 1, gives up one electron to form sodium cation, Na+, and each chlorine atom in the sample of chlorine gas accepts one electron to form a chlorine anion, the resulting compound NaCl is composed of sodium ions and chloride ions in the ratio of one Na plus ion for each Cl minus ion. Similarly, each calcium atom can give up two electrons and transfer one to each of two chlorine atoms to form CaCl2, which is composed of Ca2 plus and Cl minus ions, in the ratio of one Ca2 plus ion to two Cl minus ions. Okay. A compound that contains ions and is held together by ionic bonds is called an ionic compound. The periodic table can help us recognize many of the compounds that are ionic. When a metal is combined with one or more nonmetals, the compound is usually ionic. This guideline works well for predicting ionic compound formation for most of the compounds typically encountered in an introductory chemistry course. However, it is not always true. For example, aluminum chloride, AlCl3, is not ionic. You can often recognize ionic compounds because of their properties. Ionic compounds are solids that typically melt at higher temperatures and boil at even higher temperatures. For example, sodium chloride melts at 801 C and boils at 1413 C. As a comparison, the molecular compound water melts at 0 C and boils at 100 C. In solid form, an ionic compound is not electrically conductive because its ions are unable to flow. Electricity is the flow of charged particles. When molten, however, it can conduct electricity because its ions are able to move freely through the liquid. In every ionic compound, the total number of positive charges of the cations equals the total number of negative charges of the anions. Thus, ionic compounds are electrically neutral overall, even though they contain positive and negative ions. We can use this observation to help us write the formula of an ionic compound. The formula of an ionic compound must have a ratio of ions such that the number of positive and negative charges are equal. Many ionic compounds contain polyatomic ions as the cation, the anion, or both. As with simple ionic compounds, these compounds must also be electrically neutral, so their formulas can be predicted by treating the polyatomic ions as discrete units. We use parentheses in a formula to indicate a group of atoms that behave as a unit. For example, the formula for calcium phosphate, one of the minerals in our bones, is Ca3PO42. This formula indicates that there are 3 calcium ions for every 2 phosphate groups. The phosphate groups are discrete units, each consisting of 1 phosphorus atom and 4 oxygen atoms, and having an overall charge of 3-. The compound is electrically neutral, and its formula shows a total count of 3 calcium, 2 phosphorus, and 8 oxygen atoms. Because an ionic compound is not made up of single discrete molecules, it may not be properly symbolized using a molecular formula. Instead, ionic compounds must be symbolized by a formula indicating the relative numbers of its constituent ions. For compounds containing only monatomic ions, such as NaCl, and for many compounds containing polyatomic ions, such as CaSO4, these formulas are just empirical formulas introduced earlier in this chapter. However, the formulas for some ionic compounds containing polyatomic ions are not empirical formulas. For example, the ionic compound sodium oxalate is comprised of Na and C2O4 ions combined in a 2-to-1 ratio, and its formula is written as Na2C2O4. The subscripts in this formula are not the smallest possible whole numbers, as each can be divided by 2 to yield the empirical formula. NaCO2, this is not the accepted formula for sodium oxalate, however, as it does not accurately represent the compound's polyatomic anion, C2O4. Molecular compounds. Many compounds do not contain ions, but instead consist solely of discrete neutral molecules. These molecular compounds, covalent compounds, result when atoms share rather than transfer, gain or lose electrons. Covalent bonding is an important and extensive concept in chemistry, and it will be treated in considerable detail in a later chapter of this text. We can often identify molecular compounds on the basis of their physical properties. Under normal conditions, molecular compounds often exist as gases, low boiling liquids, and low melting solids, although many important exceptions exist. Whereas ionic compounds are usually formed when a metal and a nonmetal combine, covalent compounds are usually formed by a combination of nonmetals. Thus, the periodic table can help us recognize many of the compounds that are covalent, while we can use the positions of a compound's elements in the periodic table to predict whether it is ionic or covalent. At this point in our study of chemistry, you should be aware that this is a very simplistic approach that does not account for a number of interesting exceptions. Shades of gray exist between ionic and molecular compounds, and you'll learn more about these later. 2.7. Chemical nomenclature, learning objectives. By the end of this section, you'll be able to derive names for common types of inorganic compounds using a systematic approach. Nomenclature, a collection of rules for naming things, is important in science and many other situations. This module describes an approach that is used to name simple ionic molecular compounds, such as NaCl, CaCO3, and N2O4. The simplest of these are binary compounds, those containing only two elements. But we also consider how to name ionic compounds containing polyatomic ions, and one specific, very important class of compounds known as acids. Subsequent chapters in this text will focus on these compounds in great detail. We will limit our attention here to inorganic compounds, compounds that are composed principally of elements other than carbon, and will follow the nomenclature guidelines proposed by IUPAC. The rules for organic compounds in which carbon is the principal element will be treated in a later chapter on organic chemistry. Ionic compounds. To name an inorganic compound, we need to consider the answers to several questions. First, is the compound ionic or molecular? If the compound is ionic, does the metal form ions of only one type, fixed charge, or does more than one type, variable charge? Are the ions monatomic or polyatomic? If the compound is molecular, does it contain hydrogen? If so, does it also contain oxygen? From the answers we derive, we place the compound in an appropriate category and then name it accordingly. Compounds containing only monatomic ions. The name of a binary compound containing monatomic ions consists of the name of the cation, the name of the metal, followed by the name of the anion, the name of the nonmetallic element with its ending replaced by the suffix "ide." Some examples are given in Table 2.6. Compounds containing polyatomic ions. Compounds containing polyatomic ions are named similarly to those containing only monatomic ions, i.e., by naming the first cation and then the anion. Examples are shown in Table 2.7. Compounds containing a metal ion with a variable charge. Most of the transition metals and some main group metals can form two or more cations with different charges. Compounds of these metals with nonmetals are named with the same method as compounds in the first category, except the charge of the metal ion is specified by a Roman numeral in parentheses after the name of the metal. The charge of the metal ion is determined from the formula of the compound, and the charge of the anion. For example, consider binary ionic compounds of iron and chlorine. Iron typically exhibits a charge of either 2+ or 3+, and the two corresponding compound formulas are FeCl2 and FeCl3. The simplest name, iron chloride, will in this case be ambiguous, as it does not distinguish between these two compounds. In cases like this, the charge of the metal ion is included as a Roman numeral in the parentheses immediately following the metal name. These two compounds are then unambiguously named iron 2 chloride and iron 3 chloride, respectively. Other examples are provided in Table 2.9. Out-of-date nomenclature used the suffixes "ic" and "us" to designate metals and with higher and lower charges, respectively. Iron 3 chloride and FeCl3 was previously called ferric chloride, and iron 2 chloride, FeCl2, was known as ferrous chloride. Though this naming convention has been largely abandoned by the scientific community, it remains in use by some segments of industry. For example, you may see the word stannous fluoride on a tube of toothpaste. This represents the formula SNF2, which is more properly named tin 2 fluoride. The other fluoride of tin is SNF4, which was previously called stannic fluoride but is now named tin 4 fluoride. Ionic hydrates. Ionic compounds that contain water molecules as integral components of their crystals are called hydrates. The name for an ionic hydrate is derived by adding a term to the name for the anhydrous, meaning not hydrated, compound that indicates the number of water molecules associated with each formula unit of the compound. The added word begins with a Greek prefix denoting the number of water molecules and ends with hydrate. For example, the anhydrous compound copper 2 sulfate also exists as a hydrate containing 5 water molecules named copper 2 sulfate pentahydrate. Washing soda is the common name for a hydrate of sodium carbonate containing 10 water molecules. The systematic name is sodium carbonate decahydrate. Formulas for ionic hydrates are written by appending a vertically centered dot, a coefficient representing the number of water molecules, and the formula for water. The two examples mentioned in the previous graph are represented by the formulas copper 2 sulfate pentahydrate CuSO4.5H2O, sodium carbonate decahydrate Na2CO3.10H2O. Molecular covalent compounds. The bonding characteristics of inorganic molecular compounds are different from ionic compounds, and they are named using a different system as well. The charges of cations and anions dictate their ratios in ionic compounds, so specifying the names of the ions provides sufficient information to determine chemical formulas. However, because covalent bonding allows for significant variation in the combination ratios of the atoms in a molecule, the names for molecular compounds must explicitly identify these ratios. Compounds composed of two elements. When two nonmetallic elements form a molecular compound, several combination ratios are often possible. For example, carbon and oxygen can form the compound CO and CO2. Since these are different substances with different properties, they cannot both have the same name. They cannot be called carbon oxide. To deal with this situation, we use a naming method that is somewhat similar to that for ionic compounds, but with added prefixes to specify the numbers of atoms of each element. The name of the more metallic element, the one further to the left or on the bottom of the periodic table, is first, followed by the name of the more nonmetallic element, the one further to the right and or top, with its ending changed to the suffix "ide." The numbers of atoms of each element are designated by the Greek prefixes shown in Table 210. When only one atom of the first element is present, the prefix mono is usually deleted from that part. Thus, CO is named carbon monoxide and CO2 is called carbon dioxide. When two vowels are adjacent, the A in the Greek prefix is usually dropped. Some other examples are shown in Table 211. There are a few common names that you will encounter as you continue your study of chemistry. For example, although NO is often called nitric oxide, its proper name is nitrogen monoxide. Similarly, N2O is called nitrous oxide, even though our rules would specify the name dinitrogen monoxide. And H2O is usually called water, not dihydrogen monoxide. You should commit to memory the common names of compounds as you encounter them. Okay. Binary acids. Some compounds containing hydrogens are members of an important class of substances known as acids. The chemistry of these compounds is explored in more detail in later chapters of this text, but for now, it will suffice to note that many acids release hydrogen ions, H+, when dissolved in water. To denote this distinct chemical property, a mixture of water with an acid is given a name derived from the compound's name. If the compound is a binary acid comprised of hydrogen and one other nonmetallic element, 1. The word hydrogen is changed to the prefix hydro. 2. The other nonmetallic element name is modified by adding the suffix "ix." And then 3. The word acid is added as a second word. For example, when the gas HCl, hydrogen chloride, is dissolved in water, the solution is called hydrochloric acid. Several other examples of this nomenclature are shown in Table 2.12. Oxyacids. Many compounds containing 3 or more elements, such as organic compounds or coordination compounds, are subject to specialized nomenclature rules that you will learn later on. However, we will briefly discuss the important compounds known as oxyacids, compounds that contain hydrogen, oxygen, and at least one other element, and are bonded in such a way as to impart acidic properties to the compound. You will learn the details of this in a later chapter. Typical oxyacids consist of hydrogen combined with a polyatomic oxygen-containing ion. To name oxyacids, 1. Omit hydrogen. 2. Start with the root name of the anion. 3. Replace ate with ick or ite with us. And 4. Add acid. For example, consider H2CO3, which you might be tempted to call hydrogen carbonate. To name this correctly, hydrogen is omitted, the ate of carbonate is replaced with ick, and acid is added, so its name is carbonic acid. Other examples are given in Table 2.13. There are some exceptions to the general naming method, e.g. H2SO4 is called sulfuric acid, not sulfic acid, and H2SO3 is sulfurous, not sulfurous acid. All right. And that is it for that chapter, Chapter 2, Chemistry.